right, we're continuing to talk about the basic functions. This is section 2.6. We've talked about some of them in the previous videos, but I want to review what those were. So we've got some basic shapes that we want to be aware of, and then in the next section we're going to be using those and taking them further, like shifting them around on the graph. So it's really good if you can kind of get in your mind what these shapes are. Maybe make flashcards for these shapes and say, I know when I see this equation, I know it has this shape. So let me review those with you up to where I'm at so far. The first one is called the identity function. It's a linear equation, y equals x. The reason I know it's linear is if y is to the first and x is to the first, there's no square roots around it, there's no operation symbols, it's not squared, it's just regular old x to the first and y to the first. That's always a linear equation. So this is the most basic of linear equations. Y equals x makes this diagonal straight through the origin. Okay, and of course we know there's other lines that are moved up and down and flipped and turned and steeper, but in its most basic form, basic shape, that's the most basic of a line, just y equals x. The second one, y equals x squared, that is a parabola shape. We call that U-looking shape a parabola, and more specifically it's called the squaring function. All of these are functions I have on the board, so I could say y or I could say f of x equals interchangeably. So notice I've done that a little bit here, and then I remembered I should probably say f of x to be more specific, to designate these are known functions. So y equals x squared, I could plot some points and derive this, but it always, if you have y to the first, x to the second, you're always going to have a quadratic equation, basically, what we're talking about over here, but this is the simplest form of a quadratic equation, just regular x squared. It always makes this U shape on the graph somewhere. Again, it could be scooted over, up, flipped upside down, skinnier, wider. We've talked about those type of things actually at the quadratic before, but it's true for all of these. These are just in their most basic shape, but we can move them around and make them look somewhat different, but it'll always kind of look like this basic idea. It looks like a U, a parabola shape, when it's x squared. The third graph, x cubed, always kind of zigzags around the y-axis, so you can see that shape going on here. Now, when we get further in our book, sometimes it zigzags and it has a more pronounced swirling there, I guess, or dipping through the axis. But in its most basic form, x to the third just goes through the origin and kind of shifted or swirled around that y-axis. And again, all of these you could find some x, y values and verify these shapes, and I encourage you to do so. The fourth shape, the square root function, anytime you have a radical, a square root of x, it always has this arc looking shape, the square root function. And then the fifth one I have, reviewing where I'm at, number 5, the fifth shape is the cube root shape, the cube root of x. Anytime you have a cube root, it's almost like x cubed, only it lays down more along the x-axis. It goes this way. And so anyway, those are 5 shapes to be aware of. So I'm going to continue on with that. Okay, number 6. And these aren't in any particular order that you need to know them in, just kind of following along with the book examples. Okay, the 6th graph that we see in the book, y equals the absolute value of x. We could plot some points, and like I said on the others, this is always a good idea. Plug in something for x and say, what does that make y? So the absolute value of 0, y equals 0, so 0, 0. You'll notice so far every graph in its basic form has gone through the origin. So in its basic shape, it's centered at the origin for most of these. Plugging in 1, y equals absolute value of 1, which is 1. I could plug in negative 1 as well. And for x, the absolute value of negative 1 is also positive 1. Now that's a function. All of these are functions so far. I said the y can be repeated in a function, right? But not the x. So the x did not get repeated. I put in unique x values, but I just happened to get the same y value. That's okay in a function. I could plug in 2 and it gives me 2. I can plug in fractions. I just usually don't. But you could plug in a fraction. You get an answer. And also building off our idea of what domain and range is. Domain means what can I plug into this for X? What is it okay to plug in? So I can plug in any number I feel like. So I could say the domain is everything. I could plug in -1,000 if I feel like it. I probably wouldn't, because it would be hard to plot on my piece of graph paper without kind of counting by a large amount. But I can plug in a -1,000. I can plug in whole numbers, fractions, decimals. I could plug in square root of 3 if I wanted to, and I would get positive square root of 3. So anything goes on the X side. So we would say the domain is -infinity to +infinity. But the range is, well, what kind of answers do you get for Y? What are the Y outputs? And over here on the Y side, whatever I plugged in for X, the absolute value sign was making the Y turn into a positive answer. So the range is starting at 0 and including 0. So 0 to infinity. Only the positive numbers plus 0 are outputs for Y. When you plot some of these points, you'll see that you get a V shape. 0, 0, 1, 1, 2, 2, 3, 3, -1, 1, -2, 2. And it makes a V shape. So the absolute value of X always results in this V-shaped graph. And its function form. Notice it is a function. No X is ever repeated. All right. Next graph, number 7. The 7th graph looks like this. F of X equals. Now this one might be, it's a little different. I think this one isn't as common maybe. I don't know if you've seen this one or not, but it looks like brackets with straight lines in it. That symbol means it's the greatest integer function. Greatest integer function. In this case, whatever you plug in for X, this symbol or this operation symbol is rounding it basically to an integer. It has to round to an integer. The greatest integer that's less than or equal to what I plug in for X. Again, let me say that. X equals the greatest integer that is less than, or it can be equal to, X. Oh, sorry, Y will equal. Let me fix that. The answer for Y, sorry about that. Y will equal, the output is the greatest integer that is less than or equal to what you plug in for X. For example, let's plug in 1.5. If we were plugging 1.5 into this function, let me see, let me draw that. So the Y output, F of X or Y, will equal the greatest integer, but it has to be less than or equal to this X. So we can't jump up to 2. We can't round up to 2, which is normally what I think we normally do in math. If we have 1.5, we round it up to 2. But this one rounds it down. It has to be less than or equal to the number we plug in. So we can't go up. We have to go down. So I basically would explain this as it's a rounding down function. It rounds it down to the next integer. So it rounds it down to the Y, to the 1, sorry. The Y is 1. If I plug in 1.6, it still rounds it down to 1, 1.7, 1.8, and so on. But once I get to the integer 2, it can equal itself. So you want to keep it as large as you can, so you go with that number. So when you plug in 2, it can output 2. But you plug in 2.1, it rounds it down to 2, 2.3. So it's a rounding down function. So what's that look like when we graph it? It looks kind of odd, and it's not very flowy like the other graphs. The integers are there, like 0 is 0, 1 is 1, 2 is 2. It works for the negatives as well. -1, -1, -2, -2. It almost looks like that Y equals X thing, except in the little decimal amounts, it flatlines here. At 1.1, 1.2, 1 point everything, it stays rounded down to 0. Then once we hit 1, don't put an open circle there and say it jumps up and it can equal 1. Then at all the little decimal points about between 1 and 2, it rounds it down and stays at 1. So we put an open circle on the end of that, then we jump up here at 2. So it looks like this little stair-step ladder thing. It's very discontinuous, you know. Here it's not connected at all discontinuous. This is a very good example of a discontinuous graph where you can't just draw it in one swoop. And if you're trying to use your graphing calculator, it struggles with this too. You may see that it connects the dots if it can't pick up its pencil, and depending on which brand of calculator you have. Most of the, maybe all, won't be able to pick up their pencil and draw that, so it'll kind of connect it, which is not actually correct. It just doesn't know how to draw it any other way, because it's so discontinuous. You have to be able to pick up your pencil and draw it again. Okay, but that is the basic shape of the greatest integer function. It is a function. If I draw a vertical line, it only hits it once in any one place, because that's filled in, but that is not, so there's no repeats. We would say the domain is anything goes. You can plug in anything for x, but the range is only the integers, the set of integers. Or you may actually write out, like, it could be a negative, like -3, -2. It could be negatives or positives, but no fractions, decimals, just the integers, set of integers. All right. Okay, so otherwise, I want to show you some other graphs just to be aware of. This isn't necessarily in your section there, but it's another shape that I know you need to be aware of, so I'm going to call this number 8. And it's the rational function, 1 over x. It will come up a little bit later, but I want to go ahead and address it now so you'll have it in your notes for the shapes to know. So this is called the rational function. And if we were making a t-table, we try to plug in 0. That's usually your first thought, but 1 over 0, not defined, so it's not in the domain. So that's the one thing I cannot plug in. I can plug in fractions. Probably the next thought you would have, though, would be plug in 1. So that would be y is 1 over 1. Y is 1. That's a point. I could plug in 2. Would be 1 over 2, a half. 3 would be a third, and so on and so forth. I could plug in 100. It'd be 1 over 100. It just keeps getting smaller, infinitely smaller here. I can do negative numbers. You know, check that out. Anything. You could plug in anything else, just not 0. Anyway, after you've plotted enough of those points, and as usual, I don't have necessarily enough sample points here to draw the figure, so we're kind of speeding along, but you can take more time, pause the video, try out some other plotting techniques, and just explore this. But when you plot the points, you're going to find that it makes 2 curves. A curve up here in the first quadrant, and then a curve. It splits, sort of the graph splits apart. It gets infinitely closer to these axes, but never touching it. And we're going to talk more about that in a later section. That's called an asymptote. These lines, the graph just doesn't know what to do at 0 because it's not defined at 0. So it gets infinitely close, but never actually touching that. And does the same thing along the x-axis. So we would say the domain is everything except 0. So that's how we exclude 0, and the same thing would be true for the range on this one. All right, so that's our rational function. Fraction functions kind of look like this because of the issue with the denominator. The other graphs I want you to be aware of, let's see, that was what, number 8. Okay, let's talk about these 2 other shapes that I want you to be aware of. These are not functions, the 2 not function ones. If it's x equals y squared, that actually makes a sideways parabola shape, not a function, so we won't be talking about it as much. We mainly focus on functions, but that shape is sometimes just mentioned in the homework set, like, do you recognize this shape? So we're talking about recognizing certain shapes here. And then the last one is if you have x equals, that's kind of your clue that it's probably not a function, at least it doesn't have to be true, but I would explore that option. If it's x equals instead of y equals, maybe these aren't your functions. But this is your sideways absolute value sign, so it makes a sideways V. So I would just note that those shapes to be aware of. So those are 10 basic shapes I'd say to be aware of, and it'll help you kind of get those straight in your mind, and then we'll take it a little further in the next section.